Hey everyone, and welcome back. Ready to take off on another deep dive?
Let's do it.
Today, we're gonna explore aircraft,
Yeah.
how they're built, how they fly, all that good stuff.
Yeah.
You've mentioned wanting to get a good grasp on the fundamentals, maybe even thinking about flight training.
Yeah.
It's pretty cool that you're exploring aviation.
Yeah. I think it's one of those things, we see planes in the sky all the time, but
Right.
most of us never really think about all the things that have to come together to get them up there.
Yeah, exactly. So we've got some cool sources to work with today,
Yeah.
even excerpts from a pilot training handbook.
Nice.
Don't worry. We'll break it down. We'll make it fun and easy to understand.
It's actually more interesting than you might think. Did you know, some early airplanes were practically made of fabric?
Really?
And nowadays, some planes are so advanced they can practically fly themselves.
Wow, that's wild. So before we get into how planes actually fly, let's talk about how the U.S. makes sure that these things are safe to fly. I mean, you wouldn't want to just hop on a plane that wasn't built to super high standards, so that's where aircraft certification and airworthiness come in.
Yeah, absolutely. Safety is paramount. And
Right.
here in the U.S., the FAA plays a really big role, making sure that every single aircraft engine, even propellers,
Wow.
all meet incredibly strict safety standards.
So it's not as simple as passing a quick inspection like you would with a car.
No, not even close.
Right.
We're talking very detailed airworthiness standards
Right.
that are actually part of federal law.
Wow.
It's all about ensuring that any plane that takes to the sky is going to be safe for everyone on board.
Makes sense. So if I was building a plane in my garage, what exactly would the FAA be looking for? Is it a super detailed checklist?
It pretty much is. They're going to
Uh-huh.
dictate everything from the design and the construction materials all the way to how it's tested. And it gets even more interesting because the rules can actually change
Oh.
depending on the type of aircraft you're building. So a small plane versus a massive passenger jet are going to have to meet different sets of regulations.
So there's a whole separate set of rules for every type of plane. It's they've thought of everything.
They try to. They have categories for all sorts of aircraft, like normal utility, acrobatic, commuter transport, you name it.
Wow.
Even gliders and those cool powered lift aircraft have their own set of rules.
Okay.
And once a plane's design passes all the tests, the FAA issues what's called a type certificate, or TC. It's like a seal of approval saying, okay, this aircraft meets all the safety standards.
So it's the plane's golden ticket to fly.
Pretty much.
But what about individual planes? Do they each need their own kind of certification too?
Absolutely. Every single plane needs what's called an airworthiness certificate. It's kind of like a combination birth certificate and health record for that plane.
Okay.
It proves that it was built according to those approved designs and that it's in good condition to fly.
Got it. So no plane can just take off without proving it's airworthy. Makes sense. Okay, so before we even think about taking off, let's talk about what actually keeps a plane up in the air. So it's all about the four forces of flight, right? Lift, weight, thrust, and drag.
Those are the key players, you could say. They're like the invisible forces that are constantly at work during every flight.
Okay, let's break it down, starting with lift, because, that's what keeps the plane from, falling out of the sky, right?
Exactly. Lift is basically what counteracts gravity,
Okay.
and it's generated by the wings as they slice through the air. You know that feeling when you stick your hand out of a moving car window?
Oh, yeah, of course, my hand is flying.
That's basically lift in action.
Yeah.
The faster the car goes, the stronger that force pushing your hand upward. And that's essentially what lift does for a plane, just on a much bigger scale.
So the shape of the wings is super important for creating lift then, right?
Yeah. Oh, it's crucial. And basically what happens is the shape of the wing makes the airflow faster over the top surface than the bottom. This difference in airspeed creates a difference in air pressure.
Okay.
Lower pressure on top, higher pressure on the bottom.
Mm-hmm.
And that pressure difference is what generates lift, pushing the wind upward.
It's like the wing is tricking the air into lifting it. That's so cool. Okay, but what about weight? That one seems pretty straightforward. It's just how heavy the plane is, right?
It is, but it's not just the weight of the plane itself. We're talking about the total weight of everything on board.
Okay.
The plane, the passengers, the luggage, even the fuel. And all that weight is constantly pulling the aircraft downwards.
Right.
So it's in a constant tug-of-war with lift.
So it's like a balancing act.
Exactly.
Now, how does a plane actually move forward? That's where thrust comes in, right?
Exactly. Thrust is the force that propels the aircraft forward. And it's generated by the engine and propeller. It's what overcomes drag and gets that plane moving.
So it's kind of like a swimmer pushing off the wall of the pool to get going.
Perfect analogy. That initial push is like thrust propelling the swimmer forward.
I like it. But just like a swimmer feels resistance from the water,
Right.
a plane faces resistance from the air. That's where drag comes in, I'm guessing.
Exactly. Drag is that force that's working against the plane's movement through the air.
Hmm.
It's caused by friction and how the air flows around the plane.
So smoother, more aerodynamic planes experience less drag.
Absolutely. And minimizing drag is a big deal in aircraft design because it affects everything from fuel efficiency to how fast a plane can go.
Wow, I never thought I'd find the physics of flight so captivating.
It's pretty cool stuff.
Okay, so let's get into the structure of an airplane itself,
Yeah.
like what it's actually made of and the stuff that holds it all together.
Let's do it. Most planes, whether they're big or small, share some major components. You've got the fuselage, the wings, empennage, landing gear, and then the power plant, which is basically the engine.
Okay, let's break those down. First up, the fuselage. That's like the main body of the plane, right?
Yep, that's the heart of the plane.
Mm-hmm.
It houses the cockpit where the pilots do their thing, the passenger cabin cargo hold,
Mhm.
and it provides that structural backbone for the whole aircraft.
So it's like the skeleton of the plane holding everything together.
Exactly.
I bet fuselage design has changed a lot over the years, though, hasn't it?
Oh, yeah, you're right. Early aircraft had what were called open truss structures,
Okay.
kind of like a birdcage made of wood or metal tubing.
Wow.
And then from there, we moved on to monocoque and semi-monocoque designs, which are more common today.
You know, I've always wondered, like, what's actually inside a wing? It can't just be a hollow shell, right?
Yeah.
And what are monocoque and semi-monocoque structures anyway?
It's good. Spot on. Let's start with the wings first. They're definitely not hollow. They've got this incredible internal framework that gives them their strength and helps them hold their shape. And then we'll delve into those fancy fuselage designs.
Yeah, you're absolutely right about the wings not being hollow. They've got this internal structure that's really a marvel of engineering, kind of like a carefully constructed skeleton. The main components are spars, ribs, and stringers.
Spars. Like something you'd see at a pirate ship duel. I'm picturing sword fights on the wings now.
Not quite, though they are essential for the wing to function. Spars run lengthwise inside the wing, kind of like the backbone, and they handle most of the bending forces during flight.
So they're like the heavy lifters of the wing structure. What are they usually made of?
Well, they have to be strong, but also light, so typically they're made from aluminum alloys. But more and more we're seeing composite materials being used as well.
Right, composites. We'll get to those amazing materials in more detail later.
Yeah.
So what about those ribs? Do they give the wing its aerodynamic shape? You got it. Ribs are attached to the spars, and they run across the wing, giving it that curved profile, that airfoil shape. And they provide structural support, help the wing maintain its shape, even under stress.
Okay, so they're like the framework that defines the wing's silhouette. And what about stringers? Where do they fit in?
Stringers are smaller, lengthwise supports that run between the ribs. They provide additional reinforcement and help distribute stress evenly across the wing skin. Think of them as a network of reinforcements ensuring that the wing can handle all those forces acting on it during flight.
It's amazing how much goes into building a wing that can withstand the stress of flight. And remember how we talked about fuel tanks being located in the wings? Are those integrated into this structure too?
That's right. Often the fuel tanks are nestled right between the ribs and spars. It's a very efficient use of space, providing structural support and carrying fuel at the same time.
Before we move on from wings, I have to ask about those weight shift control aircraft you mentioned earlier. They sound like a completely different way of flying.
They are quite unique. So instead of using conventional controls like ailerons and rudders, they're flown primarily by shifting the pilot's weight. Imagine hanging from a wing and tilting your body to steer. That's the basic idea.
Wow, that sounds both exhilarating and a bit nerve-wracking. So the wings must be designed differently to accommodate that weight shifting then, right?
Absolutely. Their wings are often highly swept back, which reduces drag and enhances maneuverability for that type of flying.
It's amazing how many different types of aircraft there are, each with its own unique design and purpose. Speaking of different designs, let's move on to the next major component, the empennage. It sounds a bit intimidating, but what exactly is it?
It's not as scary as it sounds. The empennage is simply the tail assembly of the aircraft. It plays a critical role in stability and control, particularly along those vertical and horizontal axes.
So it's kind of like the rudder on a boat, keeping everything steady and going in the right direction.
That's a good starting point. The empennage is usually made up of fixed surfaces, like the vertical stabilizer, the tall fin-like structure, and the horizontal stabilizer, which kind of looks like a smaller wing. It also includes movable surfaces like the rudder and elevator.
Okay, let's break that down a bit. The vertical stabilizer, that's the tall one that sticks up right What does it do?
Exactly. It stops the nose of the plane from swaying side to side. Think of it like a weather vane in the wind. It keeps the aircraft stable along that yaw axis.
And the horizontal stabilizer, what's its job?
The horizontal stabilizer prevents the nose from pitching up or down too abruptly, so it provides stability along the pitch axis.
So those two stabilizers work together to keep the plane balanced in both the yaw and pitch axes. What about those movable surfaces you mentioned, the rudder and elevator?
You're catching on quickly. The rudder is attached to the vertical stabilizer, and it's like a movable flap on the back. When the pilot presses the rudder pedals, the rudder deflects the airflow, causing the plane's nose to move left or right.
So it's like a steering wheel for the tail, helping the pilot make fine adjustments to the plane's direction.
You got it. And then you have the elevator, which is attached to the back of the horizontal stabilizer. When the pilot pulls back on the controls, the elevator moves up, making the plane's nose pitch up. Pushing forward lowers the elevator, causing the nose to pitch down.
So the elevator controls the up and down movement of the plane. It's like a seesaw in the sky.
That's a great way to think about it. You're really getting the hang of this. And both the rudder and elevator work by deflecting airflow and creating pressure differences similar to how lift is generated.
This is all making so much sense now. You also mentioned trim tabs earlier. What are those all about?
Good question. Trim tabs are small adjustable surfaces on the trailing edges of those control surfaces we've been talking about, the rudder, elevator, and ailerons on the wings.
Yeah.
They're used to fine-tune the aircraft's trim, reducing how much force a pilot needs to apply to the controls.
So they're like little helpers, making flying smoother and easier on the pilot, especially on those long flights.
Exactly. They help maintain a specific pitch roll, or yaw, without the pilot having to constantly hold pressure on the controls. And speaking of horizontal stabilizers, there's also something called a stabilator, which combines the function of a horizontal stabilizer and an elevator into one.
So instead of separate surfaces, the entire horizontal tail section moves. That's a pretty clever design.
It is, and it often includes an anti-servo tab, which is another small adjustable surface that helps fine-tune the stabilator's sensitivity and trim.
It's amazing how much thought goes into designing even the seemingly simple parts of an airplane. Now let's talk about how these planes actually get back on the ground, the landing gear.
Without landing gear, flying would be a one-way trip. It's what provides support and stability when the aircraft is on the ground during taxiing, takeoff, and of course landing.
The most common type is wheels, right? Just like on a car.
Exactly, though.
Yeah.
Airplane wheels are built to handle much higher loads and stresses than car tires. And of course, there are other types of landing gear for different environments.
That's right. I remember seeing planes with floats for landing on water. Are there other types?
For snowy or icy conditions, some aircraft have skis, which let them glide smoothly over the surface. It's all about choosing the right gear for the job.
It's like having different shoes for different occasions, but for airplanes. Now, going back to the wheel-type landing gear, I've noticed that the wheels are arranged differently on different planes. What's up with that?
You're observant. There are two common configurations: conventional landing gear, also known as tailwheel gear, and tricycle gear, which is more common on modern aircraft.
What's the difference between them?
With conventional gear, the main wheels are located toward the front, and there's a smaller tail wheel at the back. It's an older design, and it can be a little trickier to handle because it requires more precise control from the pilot, especially during takeoff and landing.
So it's like trying to balance on a tricycle with the single wheel in the back instead of the front.
That's a great way to visualize it. Tricycle gear, on the other hand, have the main wheels behind the center of gravity and a nose wheel at the front. This setup is much more stable and easier to handle.
It's like having training wheels for airplanes. I can see why it's more popular, especially for new pilots.
Absolutely. And both types usually have steerable nose wheels or tail wheels, allowing pilots to maneuver on the ground. Some aircraft even use differential braking, applying more brake force to one wheel than the other to assist in turning.
So it's like using the brakes to help steer. That sounds pretty cool, almost like drifting a car, but in a much more controlled way.
You got it. It's all about controlling the aircraft effectively, both in the air and on the ground. Speaking of which, let's shift our attention to the heart of the aircraft, the part that gives it the power to fly, the power plant.
Yes, let's talk engines. It's the engine that makes it all possible, transforming fuel into the energy that propels these machines into the sky. What are the main components of the power plant?
Typically, the power plant consists of the engine itself and the propeller. The engine generates mechanical energy by burning fuel, and the propeller converts that energy into thrust, pushing the plane forward.
So the propeller is like a giant fan pushing air backwards and propelling the plane forward. What are those propellers made of? They must be pretty tough to withstand all those forces.
That's right. The propeller blades are shaped like airfoils, just like wings, and they create thrust by generating a pressure difference between their front and back surfaces.
Yeah.
And you're right, they need to be strong, so they're often made from aluminum alloys and sometimes even wood or composite materials.
It's fascinating how similar principles apply to both wings and propellers, all about manipulating airflow to generate force. And I know the engine also powers other systems in the plane, right?
Absolutely. Think of it like a central power station for the aircraft. The engine provides power for electrical generators, hydraulic pumps, and even things like air conditioning, keeps everything running smoothly.
So the engine isn't just about creating thrust, it's the lifeblood of the entire aircraft. Now, speaking of materials, let's dive into those amazing composite materials you've mentioned a few times. They seem to be revolutionizing aircraft design, offering incredible strength and lightness.
You're absolutely right. Composites are a game changer in aviation. They're allowing us to build planes that are lighter, stronger, use less fuel, and last longer. It's really a revolution in aircraft design.
I'm really intrigued by composites. Can you explain a little more about what they are and how they're made?
Sure. They're basically materials that are made up of two or more different components. And when you combine these components, you get a material that has properties that are even better than each individual component on its own.
So it's like taking the best qualities of different materials and blending them together to create something super strong and lightweight. What kind of materials are we talking about here?
And the most common composites used in aircraft are fiber-reinforced polymers, or FRPs.
Okay, what are those exactly?
They consist of strong, stiff fibers embedded in a matrix material, usually a type of resin. The fibers provide the strength like the muscles, while the matrix holds everything together and distributes the load, acting like the glue.
That's a great way to think about it. So why are these composites so much better than traditional materials like aluminum?
Well, for starters, they're incredibly lightweight, which means better fuel efficiency and more cargo capacity. Plus, they're also very strong, often surpassing the strength-to-weight ratio of aluminum.
So it's like getting double the benefit strength without the extra weight. That's pretty impressive. What are some of the other advantages?
Another big plus is their flexibility. They can be molded into complex shapes, which allows for more aerodynamic and efficient designs. And because they're naturally resistant to corrosion, they need less maintenance and last longer than traditional materials.
Wow, it sounds like composites are the way to go. Are there any downsides to using them?
Well, like with anything, there are some challenges. One thing is that it can be difficult to detect hidden damage. Unlike metal, which dents or bends composites, can have internal damage that you can't see with the naked eye.
So you wouldn't necessarily know there's a problem just by looking at it. That sounds a bit concerning.
You're right. It means you need specialized inspection techniques to make sure everything is structurally sound.
Yeah, that makes sense. Are there any other things to consider when working with composites?
Yeah, some types of composites can be sensitive to heat and certain chemicals, so proper handling and maintenance are really important. And repairs can be a bit more complicated, requiring specialized training and equipment.
So it's not just a matter of patching up a dent in a metal fuselage.
Exactly. But despite these challenges, the advantages of composites are so significant that we're seeing them used more and more in aircraft today, from small general aviation planes to massive commercial airliners.
It's truly a revolution in aircraft design, making flying more efficient, more sustainable, and pushing the boundaries of what's possible. Now, I know we've talked a lot about the physical structure of planes, but what about the systems that help pilots fly them? It's time to delve into the world of aircraft instrumentation, right?
Absolutely.
Yeah.
Let's step into the cockpit and explore how these sophisticated systems provide pilots with the information they need to navigate and control the aircraft.
I'm ready to put on my pilot hat. I'm guessing things have changed dramatically in the cockpit over the years with the rise of digital displays and advanced avionics.
You're spot on. We've seen an incredible shift from traditional analog instruments with all those dials and gauges to modern electronic flight displays, or EFDs. They're those large, colorful screens you see in modern cockpits.
They look like giant iPads. So
Yeah.
what are the benefits of these digital displays?
Well, they're more reliable, less prone to failure, and they can display a ton more information in a much smaller space.
Yeah.
It's like decluttering the cockpit and giving pilots a clearer picture of what's happening with the plane.
So it's like having a super high-tech dashboard for the plane. That makes sense, especially with all the information pilots need to process.
Mm.
And I bet these EFDs can also connect to other systems in the plane.
Absolutely. They can integrate with GPS navigation, autopilot weather radar, and a whole lot more. It's like having all the essential information right at the pilot's fingertips.
That's incredible. So what are the main types of EFDs?
The two primary ones are the primary flight display, or PFD,
Right.
and the multifunction display, or MFD.
Okay, so what's the difference between those two? What kind of information do they display?
The PFD is like the main screen, and it shows all the essential flight information, things like altitude, airspeed, attitude, and heading. It's like the pilot's primary source of information about how the aircraft is performing at any given moment.
So it's the digital equivalent of those 6 basic flight instruments.
You got it. And the MFD is more versatile. It can show things like navigation maps, engine parameters, weather data, even checklists.
So it's like a customizable information hub for the pilot, adapting to the different phases of flight. It sounds like EFDs are making cockpits much more efficient and user-friendly for pilots.
Exactly. They allow pilots to focus on those critical tasks of flying the plane and making those important decisions. But even with all these advancements, it's still important to understand the basic categories of aircraft instrumentation, regardless of whether they're displayed on analog gauges or those fancy digital screens.
So whether it's old-school dials or sleek digital displays, the underlying principles of flight instrumentation remain the same. What are those basic categories?
Aircraft instruments are generally grouped into three main categories: performance instruments, control instruments, and navigation instruments.
Okay, let's start with performance instruments. What kind of information do those provide to the pilot?
Performance instruments tell the pilot how the aircraft is actually performing, how it's moving through the air, and in relation to the ground. They're like the plane's vital signs.
So they give a real-time snapshot of what the plane is doing. What are some of the key performance instruments?
You've got the altimeter, which tells you the aircraft's altitude, the airspeed indicator, which shows how fast the plane is flying, and the vertical speed indicator, or VSI, which tells you how quickly the plane is climbing or descending.
So it's like having a speedometer, altimeter, and rate of climb meter all rolled into one. It's like having all the information you need to know how the plane is moving.
Exactly. And those instruments are essential for maintaining safe and controlled flight. Now let's move on to control instruments. What do you think those might tell us?
Well, if performance instruments tell us how the plane is moving, I'm guessing control instruments tell us how the plane is oriented in space, like its position relative to the horizon.
You're right on track. Control instruments show the pilot how the aircraft is oriented, its attitude, if you will.
So they're like the plane's posture meters. What's the main control instrument?
The primary one is the attitude indicator, which displays the aircraft's pitch and roll in relation to the horizon. It basically tells the pilot whether the plane is level climbing, descending, banking, or any combination of those.
That sounds like a pretty crucial instrument for maintaining spatial awareness and making sure the plane is doing what it's supposed to be doing.
It definitely is. Now, the last category is navigation instruments. What do you think those might be for?
I'm gonna guess that they help the pilot figure out where they are and where they're going, like a map for the sky.
Exactly. Navigation instruments provide information about the aircraft's position and course relative to navigational aids or waypoints.
So it's like having a GPS for the plane.
That's one example.
Mm-hmm.
Modern aircraft do often have GPS receivers that show the plane's position on a map. But there are other types of navigation instruments as well.
Like what? What are some of those other navigational tools?
Well, there's the VOR, which stands for VHF Omnidirectional Range. It's a ground-based system that emits radio signals. And pilots can use those signals to figure out their bearing and distance from the VOR station.
So it's like a radio beacon that helps pilots find their way. Are there any other types of beacons pilots use for navigation?
Yes. There's also the NDB, or non-directional beacon. It's another type of radio beacon that emits signals in all directions.
So it's kind of like a simpler version of a VOR?
You could say that. And finally, there's the ILS, or Instrument Landing System, which is a super helpful system for landing safely when visibility is low.
Ah, so it guides the plane down to the runway when the pilot can't see well? How does that work?
The ILS uses radio beams to provide both vertical and horizontal guidance, helping the pilot align the aircraft with the runway and descend safely. It's like having an invisible hand guiding the plane down for a smooth landing.
That's incredible. So all these navigation instruments, whether they're the traditional type or digital, rely on radio waves and sophisticated electronics to give pilots the information they need to navigate safely.
That's right. It's a testament to the ingenuity and innovation in the aviation industry. There's this constant push to make flying safer, more reliable, and more accessible for everyone.
This deep dive has really opened my eyes to how much goes on behind the scenes in aviation. I'm feeling a lot more knowledgeable about the complexity and all the cool technology that makes flight possible.
And we've only just scratched the surface. There's so much more to explore in the world of aviation, and it's always evolving.
I'm definitely feeling inspired to learn more. Okay, now that we've covered these basics, let's go back to those amazing composite materials we were talking about. I'd love to hear more about their history in aircraft construction and how they're being used today.
Let's do it. It's a fascinating journey from those early experiments to the widespread use of composites in today's aircraft.
So when did composites first take flight, so to speak? When did engineers start using them in planes?
You might be surprised to learn that the use of composites in aircraft goes all the way back to World War II. One of the first uses of composites was actually a soft fiberglass insulation in B-29 bombers.
Wow, so even back then, engineers were recognizing the potential of these materials.
Absolutely. And by the late 1950s, European manufacturers building sailplanes, those engineless gliders, they started using fiberglass for the main structure. They loved how lightweight and strong it was.
That makes sense for gliders. So when did we see the first all-fiberglass aircraft?
In 1965, the FAA certified the first all-fiberglass aircraft in the normal category, a Swiss sailplane called the Diamond HPV.
That must have been a major milestone.
It was, and just a few years later in 1969, the FAA certified the first four-seat, single-engine fiberglass aircraft, the Windecker Eagle.
So composites were starting to gain traction in the general aviation world.
Exactly. From there, the use of composites in aircraft construction just kept growing, driven by advancements in material science and manufacturing techniques.
And today, you see composites everywhere in aviation.
You're right, they're used in everything from small recreational planes to huge commercial airliners, even those cutting-edge military jets.
We talked about the benefits earlier, but let's recap those advantages. Why are composites such a big deal in aircraft design?
Well, as we discussed, composites are incredibly lightweight, which leads to better fuel efficiency and the ability to carry more payload. They're helping airlines save money and cut down on emissions.
So that's a big win for the environment. What about strength? How do they compare to traditional materials?
They're super strong. They often have a better strength-to-weight ratio than materials like aluminum. So you get the strength you need without the weight penalty.
It's like getting the best of both worlds. And I remember you mentioned their design flexibility as well.
That's right. Because they can be molded into those complex shapes, we can create aircraft that are more aerodynamic and efficient. It gives engineers a lot more freedom in designing those sleek, modern aircraft we see today.
It's amazing how composites are pushing the boundaries of what's possible in aircraft design. And on top of all that, they're resistant to corrosion, so they require less maintenance and have a longer lifespan.
Exactly. They're a win-win in terms of both performance and sustainability.
Yeah.
And as composite technology keeps evolving, we can expect even more innovative uses in the future.
It's exciting to think about what the future holds for aircraft design with these amazing materials. But speaking of challenges, you mentioned earlier that lightning strikes are a concern with composite aircraft. Why is that?
That's a great question. You see, with metal aircraft, when lightning strikes, the electrical energy flows through the aluminum structure. And the main concern is keeping that energy away from sensitive electronics and the fuel system.
So it's like creating a safe path for the lightning to travel through the plane and harmlessly dissipate.
You got it.
Yeah.
But fiberglass, a common composite material, is an electrical insulator. So it doesn't conduct electricity the way metal does.
So it wouldn't provide that same path for the lightning to flow through.
Exactly. And carbon fiber, another common composite material, does conduct electricity, but not as efficiently as aluminum.
So composite aircraft need some extra help when it comes to lightning strikes.
Absolutely. To protect them, we embed fine metal meshes, usually made of aluminum or copper, into the composite skin of the aircraft.
So it's like weaving a conductive layer into the structure of the plane to give the lightning a designated path to travel through.
Precisely. This helps prevent the lightning from damaging the composite material underneath. It's a crucial safety feature for composite aircraft.
That's really clever. Now I have to ask, with all the advancements in composites, are we going to see airplanes made entirely of these materials in the future?
We're already seeing aircraft with significant composite components. For example, the Boeing 787 Dreamliner has a fuselage made primarily of composites.
So it seems like it's not a question of if we'll see all composite airplanes, but when they become the norm.
You're right. With all their advantages, lighter weight, Greater strength, design flexibility, and resistance to corrosion composites are poised to play an even bigger role in shaping the future of aviation.
It's an exciting time to be following the world of aviation with so much innovation and progress happening. I'm curious, are there any other specific examples of aircraft that showcase the amazing capabilities of composite construction?
There are quite a few. One notable example is the Cirrus SR series of aircraft. They were pioneers in using composites for general aviation aircraft, and they've proven to be incredibly popular and safe.
What's so special about the Cirrus SR series? What makes them stand out? What's so special about the Cirrus SR series? What makes them stand out?
Well, they're known for their sleek, modern design, but one of the things that really sets them apart is a feature called the Cirrus Airframe Parachute System, or CAPS.
Wait, a parachute for the whole plane? That sounds incredible.
It is. It's basically a giant parachute that's built into the aircraft. If there's a serious emergency, the pilot can deploy the CAPS, and it brings the entire plane down gently and safely.
Wow, that's a game changer for safety in general aviation. It's like having a backup plan for the worst case scenario. So it sounds like composites are playing a crucial role in making these innovative features possible.
Absolutely. Composites allow for a level of design flexibility and strength that wouldn't be achievable with traditional materials. They're opening up a whole new world of possibilities for aircraft design.
You know, this deep dive has given me a whole new appreciation for the complexity and ingenuity behind aircraft. It's like peeling back the layers of an onion and discovering all these fascinating details.
And we've only just scratched the surface. There's so much more to learn about this incredible industry. What stands out to you the most from our conversation today?
Honestly, I'm amazed by how much technology goes into every aspect of aviation, from the materials used to build planes to the instruments that guide them. It's a testament to human ingenuity and our constant pursuit of pushing boundaries.
I completely agree. And it's not just about the technology itself. It's about the people behind it. The engineers, the designers, the pilots, the mechanics, and everyone who works tirelessly to make flight safe, efficient, and accessible.
This deep dive has definitely sparked a desire in me to learn more about aviation. I'm feeling inspired to explore this world further.
That's fantastic. There's so many resources available for those who want to dive deeper into aviation, whether it's reading books, visiting museums, or even taking flying lessons yourself.
Maybe I'll give those flying lessons a shot. Imagine soaring above the clouds and experiencing those four forces of flight firsthand.
There's nothing quite like it. It's an experience that truly changes your perspective and gives you a profound appreciation for the wonders of flight.
Well, this has been an incredible deep dive into the world of aircraft structures and avionics. I feel like I've gained a whole new understanding of how these amazing machines work.
It's been a pleasure sharing my knowledge with you. Keep asking questions, keep exploring, and who knows, maybe we'll see you up in the skies one day.
That's a great thought. Thanks for joining us on this journey into the world of aircraft. Until next time, happy flying, everyone.